There we go. Sorry. Thanks for your patience. Well, thank you. And we're really delighted to have both of you here.
Great to be here. You ready for us to go? Okay. Good morning, everyone. I'm Keivan Stassun and joined by Marina Kounkel. We're going to do a tag team presentation here, talking about ways in which the advent of large amounts of ultra precise light curves, spectra, and parallaxes for stars in the Milky Way is opening this new era of understanding not only of the fundamental properties of individual stars en masse, but importantly, as we'll talk about today, helping us to develop a really new understanding, a new picture of structure in the local neighborhood. Okay, so I will start by giving a sort of an overview of how the field has been progressing in terms of volume of data, specifically these ultra precise data, and how we're combining them for measurements of fundamental stellar properties, radii, masses, etc. And then I'll hand it over to Marina, who will pick up to talk specifically about our understanding of precise stellar ages and how that in turn is shaping our understanding of the history and the evolution of structure in the solar neighborhood. Okay, so in terms of these fundamental stellar data that we would like to have for as many stars as possible, and in order to understand stars individually, but also importantly in terms of populations. 10 years ago, just 10 years ago, this was sort of the state of the art in terms of precise trigonometric parallaxes, right? We had of order 100,000 good parallaxes from Hipparcos. In terms of fundamental stellar properties like masses and radii, we had of order 100 or so benchmark eclipsing binary systems that folks like Willie Torres and myself have spent most of our careers up to now working on. In terms of hyper precise light curves, time series photometry, we were not yet in the era of Kepler and TESS and so on, and so really very small numbers of stars for which astroseismology could be done, right? I mean, of order 10 to the 1, right? So that's where we were. We'll revisit these numbers toward the end, but next slide, please, Marina. That was sort of the base, 10 years ago. Here now, just a few years later, we have this incredible explosion of data of these kinds, right? So in the image there, what you see is the little yellow dot representing, roughly the volume of space around the sun that Hipparcos was able to reach. This is not to disparage Hipparcos, right? Hipparcos was incredibly important, but that was our grasp in terms of volume. Gaia DR1 already expanded our reach to the little red circle there. And now as we enter Gaia DR2 and DR3 and beyond, we basically have access to incredibly precise distances and proper motions and so on for this half of the galaxy. At the same time and within the same footprint, TESS is delivering very precise light curves for millions and millions of stars. And at the same time and within the same volume, Sloan Digital Sky Survey and other all-sky surveys of highly multiplex spectra, high resolution spectroscopy, enabling detailed spectroscopic parameters, again, for stars by the millions. And it's in combination, this data deluge of parallaxes, light curves, and spectra that is really enabling the science that we want to talk about today. So next slide. So let me give you just a feeling of what is now possible, what is now newly possible with the advent of these kinds of data. So one thing that we can now do is we can measure the radii of stars very accurately. As you no doubt know, the radius of a star is a very important parameter. It relates not only to the nature of the star itself, but also as a key informant with respect to the star's evolutionary state and age. So I want to introduce this notion of pseudo-interferometry. Let me explain what I mean. So, real interferometry is like the image of Antares that you see there, right? That's a relatively recent, fantastic technological achievement, right? I mean, that is a tour de force accomplishment to measure the radius of another star, to measure, to take an image of another star interferometrically with like, sub-milli arcsecond precision. Okay, that's real interferometry. And you can do that for like 10 stars in the sky, okay? How do we get that level of precision of stellar radii for much larger numbers of stars? Next slide. Well, now we can leverage the Stefan-Boltzmann relation, basically, because we can measure bolometric fluxes of stars, thanks to all-sky photometric surveys, and temperatures of stars, thanks to spectroscopy for large numbers of stars. So advance. Here you see two spectral energy distributions representative of what we can now do. These are two different stars where spanning from Galax in the UV all the way out to WISE in the mid-IR, we can just directly and empirically string together the bolometric fluxes of stars with high precision. And advance one more, Marina. What you see here is a comparison of the angular diameters that have been measured. These are not two random stars. These are two stars that have actually been measured with real interferometry. And you see that our pseudo-interferometric measurement of their diameters agrees perfectly with the real interferometry. So we can really do this, and we can do it with micro arcsecond precision. In fact, next slide. Here is from a paper that Karen Collins and Scott Gowdy and I did a few years ago, taking the known exoplanet hosting stars in particular and applying this pseudo-interferometric method. And you can see the typical precision that we can achieve is like a couple of micro arcseconds. Just, let that sink in for a second. The units there, micro arcsecond precision on stellar radii. And so as you see on the right, already with Gaia DR1, we were able to achieve fractional stellar radius uncertainties of like 1, 2, 3% out to distances of a couple hundred parsecs. We plan to apply this with the Gaia DR2 and now Gaia DR3, even more precise parallaxes. We will be able to extend that level of precision, couple percent stellar radii, that used to be the province only of the best studied eclipsing binaries and interferometrically measured stars, couple percent stellar radii for stars out to a volume of a kiloparsec. Okay, I hope you think that's as exciting as I do. Next slide. And we can do more, right? So for stars that happen to be transited by planets, we can take advantage of the information encoded in the transit, which basically tells us the mean stellar density. I won't go through all the math, but many of you are probably familiar with this. You can re-express the properties of a planet transit in terms of a mean stellar density. I just told you that I can pseudo-interferometrically measure the radii of large numbers of stars with high precision. Transit gives me the mean stellar density to high precision. Now I can determine empirically and precisely the mass of that star, and in turn, the mass and radius of the planet that orbits it. Next slide. And so as of Gaia DR1, again with the planet hosting stellar sample, we showed that we could achieve a few percent precision on stellar masses, With Gaia DR2 and DR3, we'll be able to achieve that kind of stellar mass precision, again, out to like a kiloparsec. Next slide. And then finally, we can now, thanks to the incredible precision of light curves made possible by Kepler and now TESS, we can see, or at least measure, the granulation, the surface granulation of stars. This was demonstrated by my former PhD student, Fabienne Bastian. And next slide. This is just to show you just how good this stellar granulation flicker is. We measure this in the basically the excess noise of a Kepler or test light curve. This is comparing the log G that we infer from granulation flicker on the y-axis versus the log G that is known astroseismically for a benchmark set of stars. And we've also showed that if you have spectroscopic metallicities, you can refine this even further. This is due to a known effect having to do with the influence of opacity on basically the vigorousness of the granulation. We can infer log G's with a light curve, with a test light curve or a Kepler light curve to like 0.05 dex. And that is comparable to what you can achieve with log G with a really good spectroscopic analysis. So next slide. If I measure the radius of a star pseudo-interferometrically, and I measure its surface gravity flickerly, I can measure the mass of that individual star. I don't need another star orbiting it. I don't need a planet transiting it. I can basically self-weigh a star by virtue of its surface gravity and its radius. Next slide, or advance. And so in terms of the number of stars that are now accessible to this level of precision with empirical measurements of pseudo-interferometric radii and of this sort of self-surface gravity mass technique, we're talking about a lot of stars. And so to my good friend and collaborator Willie Torres, who I think is on the line, I think we may be putting our EB cottage industry business out of business, but that's okay. This is tremendously exciting. And so next slide. So this is now where we've arrived in terms of the number of stars where we can do, really precise distances, really precise masses and radii, ultra precise photometry. There's been an explosion, as I'm sure you know, in astroseismology. I always say that these numbers, the leap doesn't look as impressive when you express it as exponents, but really just take a moment to appreciate what a leap this really represents. And so, having talked about fundamental properties of stars and the leap that we are experiencing and benefiting from, Marina will now talk about stellar ages and what we're learning about stellar structure in the solar neighborhood.
Right. Thank you. And I'll take over now. So as Keivan has mentioned, one of the things that has been, among other properties that has been historically difficult to measure for stars and mass have been stellar ages, in particularly ages of about a few tens to a few hundreds of millions of years. While the stars are still very young, while they're still part of embedded population, still have disks and stuff around them, we have been able to keep track of them. And through that, we have been able to figure out some of the fundamental properties that stars have when they are still just forming. And similarly to the stars, what properties the populations in which the stars have when they're still forming. And by looking at some nearby star forming regions such as the Orion complex or SCO-SEN, some of the things that have become apparent is that these star forming regions are incredibly large. They span anywhere from few tens to few hundreds of parsecs across. Some of them do have open clusters that are building up. For example, the Orion Nebula, which is the most active star forming cluster that we have in the solar neighborhood. But in large part, even so, people frequently say most stars form in clusters. Clusters in star forming regions are relatively rare. And some star forming regions may not necessarily have clusters at all, such as Taurus, for example. These star forming regions tend to form anywhere from a few hundreds stars to several thousands of stars. On the low mass end, you have, again, Taurus, which I think has only 200 or 300 stars. On the other end, you have Orion Nebula, which has on the order of 10,000 stars. And furthermore, these star-forming regions tend to be very dynamically cold. The stars that are forming inside them have the same velocity as the cloud that originally produced them. So it stands to reason that these populations will remain as co-moving groups for a considerable period of time, something on the order of maybe a few tens to a few hundreds of millions of years. And by that logic, because we know that everything is forming dynamically cold and over such large spatial scales, when we look at 10, 20, 50, 100 million-year-old open clusters, should we expect them to be completely isolated and cluster-like? Or should we expect to find an extended moving group halo around them? Well, finding moving groups have been nothing new for a long time. In the past, we have known of approximately a dozen or so moving groups within a volume of space of 100 parsecs. But very few have been known beyond that. For a fairly good reason. In order to find a moving group, you need to have information on the velocities and proper motions of the stars across the entire sky. And until recently, the best source of proper motions came from the Hipparcos survey, which didn't really have much sensitivity or resolution beyond 100 parsecs. But now with Gaia, we can push that boundary just a bit further. So we have performed hierarchical clustering on the Gaia DR2 data, trying to find clusters and moving groups and associations. And in total, going up to 3 kiloparsecs within 30 degrees of the galactic plane, we found over 8,000 different groups. And they are shown in blue. And in comparison, you see there are the yellow dots. They are tracing some of the previously known open clusters in the same volume of space. And as you can see, in terms of the spatial coverage, we are looking at something that is very, very different in scale. And in total, these 8,000 different populations account for almost 1 billion stars. And presumably, if the stars are to form together as a moving groups, they should have more or less the same age. Therefore, it should be possible to determine their age through isochron fitting for the entire stars in the population at once. And we do have quite nice isochrons for most of these populations. So you can see how the youngest populations shown in red still have a sizable pre-main sequence, and they are evolving down and fall onto the main sequence. And then as the stars age beyond 100 million years in green and in purple, the high mass stars start to evolve away from the main sequence and dying off. So with this, we are able to derive quite precise stellar ages for almost 1 million stars, which I think to date is the largest catalog of stars with known ages. And we can use this information to color code all of the populations in all of the various projections that we want to look at. So the first plot is the position in the sky that we were looking at before. Then the next panel is L versus parallax. Then the last 3 are L versus various velocity components. And it looks very busy, so let's just pick an age range and look at it in a bit more detail. So right now we're looking at the stars younger than around 30 million years. And what becomes apparent, particularly looking at the middle panel in particular, is, well, different populations have different peculiar velocity relative to one another, obviously. But more importantly, a single population can remain coherent for several dozens degrees in the plane of a sky, or in physical units for several hundred parsecs, on the order of 200. In fact, they kind of remain shaped like a string in all of the projections. So it is, again, most strongly apparent in L versus proper motion in the L component. But as you can see, we have these filamentary strings in all of the components of the phase space, including radial velocities. Now, unlike the proper motions, Gaia does not have quite as many radial velocities and they're not quite as precise. So we haven't been clustering in that particular portion of the phase space. But the fact that we do see the same coherence and smooth variations in RVs as we do have in proper motions or position in the sky shows us that these strengths are indeed quite real, that they are physical structures. And well, this is good enough when we're looking at the young populations. What about if we were to look at something that's a bit older, let's say on the order of a giga-year? Now, this is starting to look much busier, but with some careful poking and trying to tug on various populations by hand, it is possible to identify these strengths even at these ages that still remain filamentary in all of the projections. So looking at the sample as a whole and separating it explicitly as a function of age into the young stars and the old stars, and separating them out into these long strings of stars that may have a cluster somewhere inside them, or they may not necessarily have a cluster inside them, versus these more compact, more isolated groups of stars that don't have these extended halos, we find that strings are ubiquitous at the younger ages, and they tend to be very sharply defined. In contrast, only a few stars relatively are found in the more compact, more isolated groups. On the other hand, at the older ages, most stars tend to that are still clusterable tend to be in these compact groups, with still a few rather diffuse strings hanging about. Looking at it in a different way, looking at the histogram of the number of sources as a function of age. Once again, the young stars tend to be primarily found in strings, but these strings tend to go away after an age of around 100 to 300 million years. On the other hand, these more compact, more cluster-like groups don't tend to come into prominence until the age of around 300 million years. And also looking at the number of stars per given population, we find that at the younger ages, it is possible to have anywhere from a few hundred stars to several thousands of stars. But as these populations age, it is rare to find at the populations that are over a giga-year more than a few dozens of stars. So there's this envelope by which these populations starting to lose their mass, and most likely the population that we're still able to recover at the evolved ages have started out somewhere over here. So with this in mind, what is the origin of this extended structure of these strings? Well, it is unlikely to be caused by tidal stretching of previously compact clusters. Otherwise, you would expect them to start compact and then stretch out rather than the other way around. Furthermore, not every string even contains a cluster. Some of them do, as I've mentioned, some of them don't. The cluster does not have to be at the center. The cluster can be anywhere along the string if it is present. Rather, it is likely that we are tracing the primordial structure of these populations. We know that stars form in giant molecular clouds. Clouds themselves are filamentary in nature. And it stands to reason that when you have gas, you're going to start forming stars. So the populations that form inside those clouds will still going to trace the morphology of these filamentary clouds. And these populations are slowly dissolving over time. They are losing stars in the galaxy as they are relaxing. Over several dozens or hundreds of millions of years, only the densest and most cluster-like parts are going to be left behind, with most of the other extended halos being lost from being able to be identified dynamically. But some of the most massive ones, something that has the mass of the Orion complex, will be able to persist in its extended form for several hundreds of millions of years. So switching the gears a bit and looking at everything in 3D now. So right now we're looking down on the plane of the galaxy, with the sun being at the center of this plot. The galactic center is to the right of this image. Here we have the 3 spiral arms that are being captured within this volume of space. Here we have the Sagittarius arm. Here we have the local arm, and moderately referred to as the Radcliffe wave. And here we have the Perseus arm. And all of the strings that are younger than 50 million years are being traced along their spine to be placed in this 3D plot. And what we're finding is that they are not, their orientation is not random. They tend to be oriented in parallel to one another, perpendicular to whatever spiral arm they're found next to. And because these young stars tend to form in strings, that gives a suggestion that there must be some sort of dominant process that is driving this morphology. And curiously, when people look at other galaxies in high-resolution gas surveys, they're finding these gaseous feathers protruding perpendicularly away from the spiral arm. Now, again, whenever you're going to have a gas, you're going to start forming stars. So perhaps these strings of stars and these gaseous feathers are connected. Perhaps this is the driving force that is responsible for forming the giant particle clouds in our own solar neighborhood. So with that, I think we are running out of time for our portion of the presentation. And just to summarize, again, over the last decade or so, with the advancement of these very, very large surveys, such as Gaia, such as SDSS, such as Kepler and TESS, we are starting to develop a wealth of information that has already shown us a lot of incredible things, and we will be able to continue that data mine these survey data in the future. Thank you.
Thank you both. This is really amazing work. I think it's really amazing to think about all the information that we're now privy to, and really amazing, Marina, to see how when we start digging into that, we get a whole new picture of, our closest part of the universe. As amazing as it is to look out as far as we can, it's also kind of amazing to realize how little or how much we have to learn closer to home. So with that in mind, let's open it up to discussion. So Ramesh, if you wanted to go ahead and unmute.
Sure. Yeah, so my question is to Keivan, first part of the talk. It's brilliant to have so many accurate radii, but you're using the Stefan-Boltzmann law. And I can see that you get your F-bolometric happily from all the data, spectral data, but there is the T effective. And people often apply something called a color correction, or maybe they model the spectrum using a stellar atmosphere. So how exactly do you do that? Because that's where the systematic error could come in. How you relate T effective from observations to the correct T that should go into the Stefan-Boltzmann law.
Yeah, that's a great question, and it borders on the philosophical in the sense that right, the reason that we call it T effective specifically is because T effective is that quantity that is defined to make the Stefan-Boltzmann relation work. Right? So there's always a little bit of circularity with this. But to answer your question directly, when you're doing this kind of work at scale, in practice, right, what you do is you take advantage of the best temperatures, the best T effectives that you can get your hands on, which in general are going to come from a variety of sources. If you limit yourself to just those T effectives that have been determined spectroscopically, through some sort of spectroscopic analysis, then indeed, as you said, what we find is that the limiting factor on the ultimate accuracy of the stellar radii is whatever systematic uncertainties you believe are associated with those temperatures, because there are different temperature scales, there are different corrections that one might or might not apply as a function of spectral type and what have you. But in general, the degree to which these different temperature scales and corrections and what have you have systematic uncertainties, for a solar type star, say 6,000 Kelvin star, you're probably talking about 100 Kelvin of order for those systematic uncertainties, right? And so that indeed, given how good the parallaxes are, and given the fact that the bolometric fluxes can now be measured very precisely, and the bolometric flux enters into the radius calculation to the square root, it's that 100 Kelvin systematic uncertainty on the temperature that basically dominates the entire error budget. But you still end up in the domain of a few percent.
Yeah, that's amazing. Yeah, and you did show the couple of stars where your method gives a radius that agrees perfectly with the eclipse data. No, it's wonderful.
Also, to jump in on here, even when temperatures are determined spectroscopically, there are a lot of wiggle room. For example, if you're taking the spectra in the optical versus in the near infrared, then the temperature is going to be slightly different just because you have a different opacity. And there are, working closely with the survey data, there are a lot of headaches in actually measuring the temperatures precisely and what systematics are you're going to have based on which synthetic models. So even when effective temperatures are determined spectroscopically, there is still going to be some systematic wiggle room that is comparable.
Yeah,
and Marina, would you agree that of order 100 Kelvin is a fair?
Yes. Yeah.
Phil, did you want to go ahead and add to this conversation?
Yeah, so I guess kind of in the same. Hey, Keivan, nice to see you again.
Hi, Phil.
I had a question, kind of in a similar vein, but maybe a different angle, which is that, as we know, we're going quickly into a systematic dominated regime where systematics matter. And Keivan, you're very familiar with the Gaia parallaxes systematics. Hopefully, I mean, EDR3 looks a little bit better than DR2, but what other systematics are dominating our accuracy of is it the photometric 0 points? What is it that we really need to work on to try to get our accuracy as good as possible?
Yeah, good question. So again, if you're thinking about radii, stellar radii, right, there are basically three measurables that enter into that calculation directly. There's the parallax, right? The radius depends one to one with the parallax, and therefore with the uncertainty. There's the bolometric flux. The radius depends on the bolometric flux to the 1/2 power. And then there's the temperature. The radius depends on the temperature squared. So just in terms of thinking about error budget, temperature by far, the systematics in the temperature scales, as we've just been discussing, are kind of the most persistently problematic, and your radius depends on that temperature the most. So that's the number one. Parallax, that there's the one-to-one dependence, but as the Gaia data releases march on, not only have, Willie Torres and I just looked at the EDR3 systematics with the benchmark eclipsing binaries, and we no longer find a significant systematic offset, whereas in DR1 we found a big one. So the systematics are getting rapidly beat down in the parallaxes. The volume over which you can access really high precision parallaxes is steadily increasing. The radius depends only 1-to-1 on that. So I think parallaxes, I think we're good there. Bolometric fluxes is interesting because indeed, when you're stringing together Galax to 2-mass to Ys, you're necessarily going to be susceptible to some degree to those photometric 0 points. We've looked at that, and the photometric 0 points, the systematic uncertainties between photometric systems, again, say comparing Galax to 2-mass, you're talking like 2-3%. And so where your radius goes like the bolometric flux to the 1/2, that's not dominating your error budget. So anyway, long answer to say we just gotta keep working on those temperature scales.
Yeah, and another thing that in terms of the systematics that can strongly affect the data are not necessarily the data themselves, but the models. So in the past, I think it would be fair to say that models have been more precise than the data. And right now it's the opposite. Right now, the data are more precise than the models. And for example, things like isochrones. The isochrones are notoriously a bad fit to the main sequence. They're especially on the low mass end. So depending of if you want to look at the individual star or individual population, if you want to look at the synthetic spectra of stars and comparing that to the data, then the more discrepancy there is, the more systematics that introduces. And that unfortunately is something that we're still thinking about how to fix, but some of the more data-driven approaches where you have a golden standard of sources that for which you do more or less know the answer from these, albeit imperfect models, and then using these data to interpolate across the rest of the sample tends to minimize these model-dependent systematics a bit.
I totally agree with that. I think having a calibration sample is really important. I know here we've used the Gaia ESO benchmark sample and things like that extensively. The problem that we've run into is once you start reaching out to 1, 2, 3, 10 kpc, you start getting stellar populations that don't have any type of calibration, metal pore samples, and things like that, where it would be great to calibrate our isochrones against some metal pore calibration star or something like that, but unfortunately there's none out there. Yeah, absolutely.
I should quickly plug, by the way, Spherex, which I think will be hugely beneficial for a lot of this discussion, right? The prospect of having in one system spectrophotometrically flux calibrated fluxes from the optical into the near IR. We started looking at what's going to be possible when you basically just directly measure the spectral energy distribution in one go. That's going to help a lot.
So maybe we can shift gears a tiny bit and start talking a little bit about some of the structure that emerges. So I know Alyssa had a question about that.
I do.
Would you like to go ahead?
Hi, Marina. Hi, Keivan. Nice to see you. Thanks for doing this. So I just have a question about, I'm sorry, I'm looking at a screen that's up there. I'll try to look here. I just have a question about the strings, Marina. And so I've seen the papers just a little bit, but could you say for everybody how those strings are defined and whether they're robust to the technique that you use?
So originally, we've just performed clustering on the data, and we've used HDB scan, which is a clustering algorithm that is a bit more insensitive to the variation of density. For most clustering algorithms, if you have two dense clusters right next to one another, they would join them. And if you have a diffuse population, then it might completely miss it. But HDB scan is able to be a bit more invariant to the density, in that it will be able to separate two dense clusters next to one another, and it will be able to find more diffuse populations in the same run. But unfortunately, it sometimes, especially when you're looking at the more nearby stuff, truncate things a bit. For example, here we have the upper SCO, and it might separate into the upper SCO. Well, the SCO sending, it might separate it into upper SCO, it might separate it into LCC and Corona Australis and all the other parts. But as I was looking through all of these different projections, I was trying to group together things that appear to be most co-moving in all of the dimensions. So trying to connect by eye all of this extended structure. When you're looking at more extended regions, then there isn't quite as much fragmentation. So I'm not sure.
The answer is that you did most of this by eye, is that right?
Yeah, so originally there has been a sample of stars that has been clustered, and then looking at that sample, kind of start using this as a starting point. I would look here, for example, there's an overdensity. All right, let's select this overdensity and see where it lands in all of the other projections. And through this, we are able to separate them out.
Got it. Thanks.
Other.
Morgan, you're muted, by the way. I do see one other
Oh,
hand.
I'm so sorry. I was talking, but I was muted. Yeah, thank you. Go ahead, you.
Yeah, thank you. Yeah, it's great talk here. It's very interesting to see the relation of these stars in groups and strings with the molecular clouds. I have just 2 comments here. So the first one that these strings in this with this coherent velocity just reminds me of the velocity coherent structures in molecular clouds, which is done by inspecting the position velocity of the molecular cloud with the some spectral lines. And they also found that these filaments with coherent velocities. But I think they are on 2 different scales. And for those structures, some about within a molecular cloud, we're on several parsec scale. But for the strings and the groups you showed, it's about much larger. So, but it's still very interesting to see this similarity here. And
Yeah. So in terms of clouds, clouds can get quite large. There was a survey by Catherine Zucker of all sorts of different types of molecular clouds, and there are some that are more compact, but there are some that are really, really, really huge. And even in those large ones, I think the velocity dispersion is still on the order of just a couple of kilometers per second.
Yeah, so it could be very interesting to see whether there are some intrinsic relations. Another point is the size and velocity dispersion of molecular clouds, which is often called by as the Marsden's laws, and it is related to the intrinsic turbulent physical properties of turbulence, and also I've seen a paper recently on in Nature Astronomy on studying the mass and the velocity dispersions of the star clusters in these star-forming regions, and they found such a very similar relation to the Larsen's law, which is very interesting. So I think it would be interesting to see this size and velocity dispersion relation with such a large volume data.
Yes, absolutely. And we have looked at it in a couple of regions. And for the most part, I think they do tend to follow Larsen law. But one of them, the reason I went to the slide, here we have Orion in this red blob. And in Orion, there have been several supernovae, and they actually inject turbulence into the gas and stars. So there we are actually able to see this injection of turbulence in the velocity dispersion of the stars. So even so, it's still quite low. It's less than 5 kilometers per second there across the entire Orion complex, but we are able to see this extra bit of turbulence that is from the supernova injection.
Yes, so you're suggesting that this supernova injection will change the relation?
Oh yeah, so it yes, as the supernova has changed much of the morphology of the complex. It has triggered star formation. It has allowed the formation of the Orion Nebula, and it changed the overall velocity dispersion. Yes.
Okay, thank you very much.
Ramesh, yeah, go ahead.
Yeah, sorry, I don't want to dominate the discussion.
No, this is great.
But you know, every time I listen to a talk that involves Gaia data, I just walk away thinking what a miraculous, project it is.
Yeah.
And today, the big thing that caught me was in one of your early slides, Keivan, you showed how the DR1 data gave us information up to some distance. And then by the time you go to DR2, DR3, it's a huge increase in volume. And when you think of it as volume, going as distance cubed, it's just mind blowing. Why is it so good? As you increase the duration. I don't mean why Gaia is so good. They designed it great, but I'm just trying to understand, what is it? Are we just getting a better handle on systematics? Because root n to me doesn't seem like it can grow this fast in volume.
Yeah, that's a good question, and I will confess that my knowledge of the technical details of in terms of the detectors and the scanning strategy and so on is limited. Obviously it's not like Gaia was on some larger or different orbit or something, right? I mean Gaia, like Hipparcos, is on the same 1 AU baseline that Hipparcos was. So that right there tells you that the advance is really entirely in terms of technique and detector sensitivity. But truly, at a more technical detail, I don't have the answer for you.
Yeah, somebody probably knows in the audience. Sure, you get more data if you wait till 2022 compared to 2017. But the relative size of those two volumes is at least, as a dumb theorist, I'm kind of struck.
As I understand it, it isn't like root time, right?
No,
maybe someone who actually knows can describe that in detail.
So sensitivity is a big thing. Gaia is around 100 times more sensitive, maybe even 1,000 times more sensitive than Hipparcos. So that alone gives you more stars that are further away. But also it has much better centroiding, so that you are able to keep track of the position of the stars over time much better. A big systematic in trying to do this analysis is that all the stars along the same line of sight are going to be moving in the same direction, or as from the effects of the parallax. And so by using the two different arrays that operating simultaneously, they're able to get better centroiding, better pixel scale and everything else. So that gives you a better precision as well.
Catherine, did you want to jump in here?
Yes, I have a question for Marina. So my understanding is that you think that many of these strings have to form in situ, so they have to form in these highly elongated clouds. And so thanks for the shout out. I do study a lot of highly filamentary molecular clouds. In particular, I know these are not too common in the galaxy to get these highly elongated filaments. I estimated there's on the order of thousands in the whole Milky Way. And so I'm curious if you have other evolutionary pathways for how to form these strings when they're not being stretched out by like galactic rotation or differential rotation as they evolve.
Not that many other than forming in situ. It makes it a bit easier that we are averaging over time. So even so, you might have one or two forming at a given time. As you are averaging over the 50 or 100 million years, you're certainly going to find more of them that are still being remnants. So the clouds themselves tend to be fairly short-lived. They go away after a couple of million years, or if less than that. But these strings of stars we're able to keep track of for much longer. So that is probably the best way I can think of to reconcile the difference in numbers.
Sorry to interrupt, but the argument, so in this diagram right here, so this is going out to like 2 kiloparsecs. So is the argument still that all of these strings are forming in highly elongated clouds, given that they're so young, right? So they're less than 50 megayears.
Yes.
So you're saying it's a consequence of averaging over time, or?
Yeah, so here, almost all of them shouldn't have any gas anymore. So there are some exceptions, of course. So here we have Orion, well, Orion is here, this is Perseus, and Perseus, for the most part, has depleted its gas, just has a couple of clouds left over. Ophiuchus is over here. There are a couple of other gas bearings, kind of the reddest ones, still might have some gas left over, but everything else doesn't have gas anymore.
But you've looked at very, very young clusters, I'm assuming, as like analogs, and is the gas also very highly extended as well? So that would be something to look for.
Well, in Orion you do have a long filament, but half of Orion has already depleted its gas.
Okay. Okay. So we should talk a little bit more about that offline then.
Yes.
Yep. Thanks.
So I had a bit of a related question. And it's thinking a little bit about sort of the differentially rotating frame of reference. So, I do hydrodynamic simulation. Something that we sometimes do is we put ourselves in that differentially rotating frame and we look at the time evolution. So can we do that sort of analysis here and ask like how these stretch and unstretch over time? And how that traces these filamentary structures. And I was wondering, as we look at sort of in the age bins, are there reasons why we might not find something filamentary that is a gigayear old, for example? And maybe like, are there, selection isn't quite the right word, but it's like, are there properties of these groupings that allow, clump white-like ones to persist for longer so that we still see them as groupings, and string-like things to stretch out over time? So maybe you can talk a little bit about how these evolve in the galactic field.
Sure. So the rotation is happening in this direction. Or I don't remember, I think it's in this direction. So as things are orbiting, this bit is going to be pulled less strongly or more strongly than this bit. So things are going to be start to, if they are originally forming perpendicular to the spiral arms, then differential rotation would tilt them eventually over time. And of course, there are tidal forces that are happening, that are acting on the individual clusters and individual strings, and they would disperse the populations further. So tidal forces, you tend to develop these tidal tails typically by the age of around 100 million years. So these are a bit too young to really have experienced many of these tides. But there have been some studies that are actually trying to find tidal tails around clusters such as Hyades and Pleiades. So following those, it is starting to become possible.
Yeah, absolutely. But like, even as we look at the changing morphologies between your very young groups and your older groups.
Yes, in terms of changing morphology, yes, for the most part, as a galaxy completes one orbit, for the most part, the velocities of these more extended stars tend to be too different from the parental velocity of the structure that would have been originally there, so they are no longer recoverable through clustering. As we are able to determine more ages of stars, even if they are not necessarily part of the moving group, such as through astroseismology, chronology, then we perhaps might be able to reconstruct some of these populations a bit more, and then see how exactly all of the stars that have originally been part of our populations being dissolved into the galaxy.
Fantastic. To both of you, Keivan and Marina.
Can I
of
ask,
course, sorry.
Marina? So Marina, just because I know this is a question that you get often, and in case any of the folks in the audience later end up wondering this question to themselves, I thought maybe I'd preemptively ask you the question. Sometimes, right, in astronomy, we see string-like structures that are that are not real, that are the results of of errors and projected along the line of sight, fingers of God type things. How do you know that that's not what you're saying?
Here in the local volume, we really have incredibly precise data. Somewhere at the Perseus arm and Sagittarius arm, where you do have a bit more uncertainty in distance, then the exact orientation of the string may be a bit more up to the debate. But in the plane of the sky, you wouldn't expect fingers of God extended lying along in plane of the sky.
Mm-hmm. Mm-hmm.
Great, thank you. Thanks again.
And to both of you, we have, a couple minutes. What are your thoughts? Like, where do we go from here? What are you most excited about next? Like, as a last word, there's such richness here and so much to talk about, but.
Marina, you please.
Yeah, so right now we are in the process of starting SDSS-5, which is going to observe spectra of millions of stars. And this will include 100,000 young stars. And we already have been able to observe several thousands of them in just the first couple of months of operations. So as we are getting more radial velocities, that are going to be as precise as the promotions that Gaia provides, we are able to explore the full phase space and actually start looking at how these individual star forming regions evolve over time.
That's really beautiful. That's really beautiful. Well, on that note, let's all express our gratitude to our speakers for joining us remotely. This has been a really fascinating hour. Thank you so much. And thank you everyone for the great discussion.
Thanks for the opportunity. Bye-bye.
Bye. It's really wonderful to have you all.
Thanks again.
Mm-hmm.